Okay, so it's time to get started. Hello everyone. Today we have dismissed lecture by Professor Kieron B. So let me briefly introduce you. Although I'm sure that most of you already know him through your work. So Professor Kieron B. He is originally from Ireland, so he did a bachelor degree with at Trinity College Dublin, and he graduated in 1985, and then he moved on to do PhD with Professor Walter Kohn, as you know, the founding father of dense functional theory and electrical at UC Santa Barbara. So he graduated with a PhD in 1989, and then he was affiliated with Rutgers University. Before that, he was at Tulane University with Purdue. So that's when you had this PV functional. And then he moved on to become a professor at Rutgers University in 1996. And around this time, I had to actually work with him as a postdoc more than 20 years ago. But hopefully, we will have now again this collaboration things going on.
He turned me down.
Well, anyway, so he went on to move to the UC Irvine in 2006, and from then on, he is in California, Southern California. Now he's a chancellor professor as well as distinguished professor at UC Irvine. So many of you already know that he was one of the main figures in developing these exchange correlation functionals that are both practical and accurate. So PV, generalized gradient approximations. But then what I'm surprised, impressed with his work is that he was pioneering this combination of machine learning and then dense functional theory. So you all know these two areas are really playing an important role in modern science and technology. So I'm really honored and excited to have him in KAIST. By the way, so he was in KAIST about 5 or 6 years ago, but at the time I was in Japan, so I couldn't talk to him at the time. So I'm really glad to see him in KAIST campus. So let's welcome him and for this 2-day lectures.
Thank you very much. I'm very happy to have been invited. I love coming to Korea. I have a long-term collaboration with Yonsei University, and I always enjoy being here. And but it turned out that on this trip, I was a little unlucky. I didn't do my homework, and it turned out I'm not actually a U.S. citizen. I grew up in Ireland, and it turned out I needed a visa to come to Korea for the first time, I think, this time, and I didn't have it. So my trip here was about 14 hours longer than it was intended to be. I got an electronic visa, and it came through 8 minutes too late for me to get on my plane. But I'll tell you tomorrow that I made good use of the 12-hour delay. Okay, so we have 4 lectures lined up about density functional theory and machine learning. The first one today is just density functional theory. The second one is about just machine learning. And then tomorrow's lectures, we start combining them and seeing how they work together. Yes, and as Professor Kim was saying, these are 2 of the biggest topics topics, I would say, in sort of science and technology at the moment. All over the planet, governments are investing heavily in DFT calculations. And so are the high-tech companies. Samsung is, Google is, all the big ones in the US, because of the importance for, mostly for materials design. It used to be that it was for drug design, but materials is now become much more. Okay, so mathematical form is that we have a Hamiltonian for the electrons. It's got a kinetic energy, an electron-electron repulsion, and a one-body piece. And the only thing that differs in all the molecules and solids that we look at is this electron nucleus attraction. The Z is the charge on the nucleus, and the R alpha is the position of the nucleus. And that's the only thing that's different in all the different systems that people look at. And at the bottom, it's a bit hard to see, is the Schrödinger equation, but it's a very difficult equation to solve because you have, let's say, n electrons, and n might be a few hundred electrons or even a few thousand, and the electron-electron repulsion couples all these coordinates together. So it's a complicated quantum many-body problem. There are fermions on top of that. So it becomes exponentially hard to solve as the number of electrons goes up. And we have the variational principle that we can get the ground state energy by minimizing overall allowed wave functions. Okay, so DFT basics. So density functional theory begins with publication in 27 of papers by Thomas and Fermi. Thomas's paper doesn't mention the Schrödinger equation because I don't think he's heard of it. And this is the original paper. And he approximates the kinetic energy with what we would now call a local density approximation, this TS local, and the Hartree energy, which is just the classical self-repulsion of the electron cloud. And by writing those two approximations, you can write down an expression for the energy that depends just on the density, and you can minimize it and solve for the density and then get back out the energy. And it's good to within about 10% for the electrons in materials, but the energy of the total energy of the electrons is a huge number, and it's tiny little energy differences that we need to get right in order to do chemistry and materials accurately. And in particular, Edward Teller proved that molecules don't bind in Thomas Fermi theory. If you bring two atoms together, the energy does not go down. And if molecules don't bind in your theory, it can be hard to get a job in the chemistry department. In '64, Holmberg and Cohn wrote their famous paper in which they prove that there is an exact principle, variational principle, for the density. And the modern way of writing this is something called the Levy-constrained search formula. And you simply write the minimization as a two-step process. Minimize overall wave functions, giving the density, and then minimize overall densities. And when you do that, the one-body piece sticks out because the one-body piece only depends on the density, and you can put everything else inside this F. It's often called the universal part of the functional, and they prove that it's only a functional of the density. And back in the day, they were explaining that, so this shows you that Thomas Fermi theory is actually an approximation to an exact theory. And then the next year, Walter Cohn and Lou Sham write these Cohn-Sham equations, and they imagine a fictitious set of non-interacting electrons with the exact same density as your real system, and they're still fermions, but they don't have interaction between them. And this is called the Kohn-Sham equations. This is the Kohn-Sham scheme. And what's useful about it is that once you write that set of equations, you can see that you only need to approximate a small fraction of the total energy, called the exchange correlation energy. And not only that, you can show that the potential inside these equations can be gotten from the functional derivative of that piece of the energy. So if you have a formula for this guy, or the exact guy, you can feed it into these equations, you solve them self-consistently, and out will magically pop the ground state density, and you can put it back in and get the ground state energy of the real system. So these are fictitious. This is the helium atom ground state density. This is the external potential, -2/r, that the two real electrons feel. And this red line is the exact Kohn-Sham potential of the helium atom. If I doubly occupy the 1s orbital here, I get the exact ground state density of helium. So the Kohn-Sham scheme is a way of bypassing all a lot of the expense of solving this difficult differential equation, and in principle, with the exact functional, gives you the exact results. In practice, of course, we always need to approximate this exchange correlation. A lot of today's basic approximations start from these forms that we already found about 25 years ago. The local density approximation for exchange was already in Kohn-Sham's paper in '65. For exchange and correlation, for exchange, it's just this very simple formula. In the 80s and 90s, along came these generalized gradient approximations, where you use not just the density, but the gradient of the density. And then in '93, Axel Becker suggested these hybrid forms where you mix some Hartree-Fock exchange with GGA exchange. And these are more accurate still. Now, today's approximations there are many more sophisticated things than these ones, but almost all of them have some of these ingredients. Here's some cool DFT applications.
그렇죠. 근데 GPT 4.0은 얘가 대답할 때는 아예
So this one, sadly here, no, this was good. There's been, over the last 10 years roughly, or less, we've had these new high temperature superconductors. They are BCS type superconductors, but they are materials under very high pressures. And these were first discovered from a Chinese group running DFT algorithms on a search under pressure, hydrogen sulfide. And they predicted TCs of about 200 Kelvin, and the next year a German group made them, and they were as high as they're supposed to be. This was a recent claim, I think last year, where they really claimed to have gotten to room temperature superconductivity with these high pressure materials, but it's since been withdrawn. That's an interesting story you can read about. This little guy here, I think this is an artist's impression or a photograph of the guy over Jupiter. So it's a satellite called Juno, and every 57 days, due to a stuck valve, it was supposed to actually circle Jupiter quite closely. Due to a stuck valve, in fact, they're in a big elliptic orbit. Every 57 days, it comes close to Jupiter. And it's measuring the gravity of Jupiter. And there are lots of people running big calculations of the interior of materials in the interior of Jupiter, predicting the equation of state under the intense temperature and pressure. It's something called warm dense matter. And every 57 days, they get an update on more accurate readings on whether or not their equation of state is working. This is a famous thing called a volcano plot. Friends of mine, Jens Norskov, and others in Denmark, figured out a better catalyst for the Haber-Bosch process using DFT calculations on surfaces, so putting molecules on surfaces, and they found a better catalyst that had been estimated. There have been 25,000 experimental attempts to do that, and they found it using DFT calculations, and then it was made and it works. This is the gilt-head sea bream from the Journal of Physiology, and in that journal they talk about what happens to the poor fish as you acidify, put in more CO2 into the water. It's not the amounts that you worry about, just tiny traces of extra CO2 affects the ability of the fish to smell, and it uses that ability to avoid predators, so they all get eaten. And to figure out how it does the smelling, they do DFT calculations on these olfactory molecules. And this is me doing some experimental DFT research. It's rather well known that I like coffee. That's another reason I like coming to Korea. And somebody had done DFT calculations to tell you how much the hardness of the water with which you make the coffee affects the taste of the coffee. You can do that with DFT. So it's in lots and lots of things. This is a picture, I think it's the most recent one. I haven't checked lately. So NERSC runs the supercomputers of the US Department of Energy. And a bit surprising, this is the allocation of time of all the DOE supercomputers in the US. And you see that DFT now takes up about a third of all supercomputer time, more than climate models. So that does give you some sense of how important it actually is. The tutorial that we did a few years ago with a very good physics student. But for no matter what your background, if it's chemistry or physics, engineering, materials, if you've learned some quantum mechanics, you can read this article. And then on, if I know you younger people don't actually read anything anymore, right? You watch videos. So I got all these old people to make videos for you. So there's a YouTube channel teaching the theory and density functional theory where they give pedagogical lectures. You only have an hour, it's about 24 hours worth. And these are the people who have developed it, like Hardy Gross and John Purdue and Wai Yang. Okay, so the advanced topics. These are, so my next thing is going to go through 6 advanced topics briefly, right? Highlighting, and it's all to do with research I'm currently involved with. Do we have any questions on what I've said so far? And we'll take you, I'll sort of stop after about 50 minutes and we'll have a little break and then we'll do the second. So the first one here is excitations. Yes, and it is excitation. Good. So what I showed you is basic ground state theory. And that's what people use most of the time. And in fact, if you look at all these codes like VASP, and Gaussian, and codes like that, people mostly just extract the energies as a function of the nuclear position. Very often, people look at the cone-sham eigenvalues in the orbitals and they interpret them as excitations of the system. The unoccupied ones are excitation. And this is actually a very useful way to look at things. And much of the time, it will be just, it will be a good approximation. But it's not formally correct. And in molecular systems, we now have time-dependent DFT, which allows time-dependent external fields. So you can turn on a laser with a given frequency, and the linear response yields the optical excitations of the system. So optical excitations meaning you take the neutral molecule and you excite an electron, but the number of particles doesn't change. So TD-DFT was created by my friend Hardy Gross and Eric Runge in 1984, a little time ago. And nowadays, something like, there are, let's say, up to several thousand TD-DFT papers each year using this, mostly in chemistry, but also some in materials. I forgot to mention that I was sort of doing an estimate. It looks like there's at least 50,000 scientific papers every year that like the Cohen-Sham equations, where they solve Cohen-Sham equations for materials. So it's like a few percent of all science is DFT. Now in solids, people use something called GW, and that gives quasi-particle excitations. It gives you an approximation to something called a spectral function, which is not the same as the optical excitations. They're the excitations when you add or remove an electron from the system. Okay, so recently, actually so recent that it hasn't even been submitted yet. I was supposed to be working on it last night, I think. We're just finishing this off. So a new alternative to TD-DFT has gotten popular called ensemble DFT. And that, interestingly, was also created by Hardy Gross in collaboration with Walter Cohen a year or two after created time-dependent DFT. And in a week or so, we'll put on the archive some new exact conditions that ensemble density functionals need to satisfy. But the approximations are getting better and better in this area, and people are beginning to do real molecular calculations. And there'll be a workshop in school. I'm not sure, I think the deadline might have just closed, but I think you can probably still apply on TD-DFT at Rutgers Newark in the summer. Okay, so that's one topic. Another topic, yes, these are a little out of order because okay, so this is called SCAN. So this is a new functional that, how many people have heard of SCAN? Okay, so this is a new functional John Purdue's group from, I guess now it's a while ago. Janwei's son, Adrian Wuzinski, and John. Strongly constrained, appropriately normed. It's a meta-GGA, which means it depends on the orbital kinetic energy. It's more accurate than PBE for many purposes. It's often not quite as accurate as a hybrid functional, but if you're running a materials calculation, it can be a lot faster than running a hybrid because it doesn't require the Hartree-Fock exchange. So it's usually a lot faster than running HSE06. It doesn't give you as good a gap as something like HSE06, but like I say, it's a lot faster. And many people are beginning to use it for materials calculations. Now, I should mention that the original version of SCAN has a few issues with converging the density for molecular calculations, or when you have atomic orbitals. But since then, there's this thing called R2 scan, regularized scan, which converges much more easily. It isn't that there's really a problem with scan, it's just harder to converge. You need very big density grids. Okay, so that's the most recent non-empirical functional from Burke. And it's based on satisfying 17 exact conditions that have been known in DFT, and the paper actually claims that these are all the known exact conditions. Well, it turns out that turned out to be all the remembered exact conditions, remembered by John Purdue, because it turned out there were at least two that he had proven 30 years earlier that he forgot when they wrote this paper. So we noticed this, and we started thinking about the whole business of exact conditions versus fitting that is often done in chemistry. And these non-empirical functionals are often less accurate for molecules, but they work for both molecules and materials. And so there's a recent preprint that hasn't been accepted yet with Ryan Pedersen, a very good physics student of mine. And this picture here is of a made-up density. The blue line here is, we call it a Gedanken density. And it's a density we made up to cause problems. So it's for 2 electrons. And if you feed this density into the Li-Yang-Par correlation functional, it turns out the correlation energy will be plus 37 millihartz. Now, a really basic rule of quantum chemistry is that correlation energies are negative. Because of the variational principle, if you do a Hartree-Fock calculation, you get some number. The correlation energy is how much more negative the true energy is. So you feed this density into Li-Yang-Par, and you get 37 millihartz. Now you feed it into PBE, and you get minus 17. And the reason you know that you'll get a negative number is PBE functional automatically guarantees that the correlation energy is negative no matter what density you put in. However, this Li-Yang-Par correlation functional has been used for 30 years in chemistry. So in, I think, at least 150,000 papers, nobody has ever complained that their correlation energy was positive. The reason this is happening is because we made up this density. If you put in, we can show that if you put in any Coulombic density, any density from a real material or molecule, Li-Yang-Par will give you a perfectly reasonable negative correlation energy. Which, if you follow the logic, then says that requiring non-empirical functionals to always give negative no matter how crazy the density is in some ways overkill. And so this paper is about how it is that in chemistry today we have hundreds of perfectly respectable approximate functionals that have been fitted to molecular databases that violate lots of these exact conditions and still give reasonable results. And the reason is because they do not violate them for Coulombic densities. And this is one of these tables where you're checking all these conditions, and we find that under sort of standard Coulombic conditions, the empirical functionals still satisfy. And this explains why those functionals are still useful. And what's really going on is the non-empirical functionals of Jean Perdue, which satisfy all these conditions. What are the conditions doing? They're making up for the fact that we don't have databases for materials. Materials you can show are qualitatively different from molecules, and we do not have accurate data. There's almost none. No high quality data like we have for molecules. We have it for molecules because of quantum chemistry. We don't have the equivalent in materials. And in the absence of that, these exact conditions are allowing you to interpolate to include both the materials and the molecules. Whereas the chemistry functionals are usually giving very bad results for materials. My time. Quick mention of this because the first principle is semi-classics. So for 20 years, I've been trying to find ways to derive density functionals from first principles. And it turns out, so a systematic derivation of the approximation. And it's a possible route toward chemical accuracy. And you can show that the density functionals are actually semi-classical. Local density approximation that they all start from, you can prove is an expansion in Planck's constant. And you can also show that the GGAs that we currently use do not give quite the right answers. They try to. And you have different corrections for molecules and solids, which is why you have these different sets of approximate functionals. Has anybody here used PBE Sol? You, right? So that was designed, we designed it to give you better lattice properties and phonons. And it actually, one of the conditions used in that comes from the semi-classical analysis. And then other conditions for correlation were built into SCAN. It's in the 17 exact conditions. So we've been using them to improve functionals. This we can skip. So a very good, before I get to that, yeah. So orbital-free DFT is something that's going to come up quite a bit in these lectures. So the original Thomas Fermi theory didn't use orbitals. Kohn and Sham introduced this scheme of orbitals. But there's a cost, and the cost is n cubed, where n is the number of electrons. You have to still solve the Kohn-Sham equations. If you knew the kinetic energy as a function of the density of the Kohn-Sham electrons, you could bypass that. And then probably solving the Poisson equation for the Hartree potential becomes the most expensive part. And Thomas Fermi theory has this form, but we said it's not accurate enough. And for about 100 years, people have been trying to do this. But no one has been able to do it accurately enough for modern materials simulations. And it's harder than approximating the exchange correlation energy because the kinetic energy of the electrons is a much larger number. And also, you need its functional derivative put into the Euler equation to solve for the density. and it must produce the quantum shell structure. When you solve the Kohn-Sham equations, you get atomic, orbitals, molecular orbitals with the shell structure, the correct shell structure, more or less, of the system that you're looking at. If you just have something like Thomas Fermi theory, there's no oscillations, there's no shell structure, there's lots of things that are wrong. This guy here, Pavel Oken, was a chemistry student who just finished a little while ago with me. And again, this is on the archive. And we do these semi-classical expansions for slabs. And what we're looking at here is the error in Hartrees, in millihartrees, for the kinetic energy of the electrons in one of these slabs. So this is in Hartrees, so these are very large numbers. These are the errors that Thomas Fermi theory makes. In this case, they're pretty small. This is Thomas Fermi theory on the exact density, so it makes a slightly smaller error. If you do the gradient expansion or even a modification of it, you do pretty good, but these are still tens of millihartrees, so this is not chemical accuracy. But when we do this semi-classical expansion and we do it correctly, you can see that we start getting down to, so chemical accuracy is about 2 millihartrees, and here we're at 4 or 5. But what's interesting, because it's an expansion in H bar, we can always go to the next order. That's the thing will allow us. So we can calculate the next order, and you can see that all the errors are now below a millihartree. So for this slab geometry, so it's not a real three-dimensional object, it's uniform in two directions, but has a potential in the third direction. So you can test anybody's orbital free density function for this, and we're sort of guaranteed to always win. Because even if something could have errors as small as this, we would always add another term. So these errors are 10 times smaller or more, 20 times smaller than the errors in today's exchange correlation function. So if we could do this for an arbitrary shaped potential, we would have orbital free DFT. The criterion is that you need to make the errors in this part smaller than the errors in exchange correlation. And these terms here are all derived as expansions in H bar, not made up anyway, like things like PDE. Density corrected DFT. This is the work with Professor Sim at Yonsei. This is all within, so far, pretty much everything we've done has been molecules and not materials. And what we find is that there are many cases where the approximate functionals give you bad densities. So when you have an approximate functional, you're using it in two ways. You're using it to calculate the energy, but you're also using it in the Kohn-Sham equations to calculate the density. Most of the time, for most things, the densities are pretty good. But occasionally we find these classes of problems where the density is bad. And in the molecular cases, you can use the Hartree-Fock density instead. This was a recent article that Anji wrote, showing all these different chemical systems that are all improved by doing this simple trick of evaluating the functional on the Hartree-Fock density instead of the self-consistent density. And in particular, what was noticed is that these water clusters, as they get bigger and bigger, you get substantial improvements. Here's the DFT errors, even when you put in dispersion, and then here's the Hartree-Fock DFT, and you add the dispersion, and you get almost no error. And that's it. And so recently, just at the start of this year, Suwon, who's now gone off to work for Samsung, created this functional using R2 scan on the Hartree-Fock density and putting in dispersion corrections. And as far as we can tell, this is the most accurate functional for bulk water, which is a terribly important thing, and obviously lots of bio applications. And it's not only good for the most accurate functional we have for bulk water, it's also the best we have for we put other things in water like aspirin. The interaction with the water is most accurate in this functional that you developed. And this appeared in Nature Communications just a little while ago. Okay. I think I'm not going to say much about strong correlation. We'll get back to that, but this is going to become a big part of the last talk. So I'll go over that again. But one important thing just from a few years ago was we created this thing called conditional probability DFT, which is more accurate than normal DFT, but a little more expensive to run. And this was in order to do strongly correlated systems. This is Steve White, who's at physics in Irvine, and he invented this thing called DMRG, which does strongly correlated systems. The reason this has now become important is because it has allowed us to put in the temperature dependence in the PBE functional. We can actually just calculate its temperature dependence, and people who do these calculations, like for that Juno satellite, need to know what this temperature dependence is. The exoplanets. And here, John Kozlowski, who's finishing soon with me. These are his pictures of what happens when you change the temperature in the PBE functional. So DFT has sort of revolutionized warm dense matter over the last 10 or 15 years. Well, one of the big questions has been, so these are electrons at temperatures from about 30,000 Kelvin up to 10 million. So one of the big applications is there's this huge machine at Lawrence Livermore called the National Ignition Facility, and they've gotten to the point where they get more fusion energy out than laser energy. They take a little capsule and they blast it with 200 of the world's largest lasers in order to do controlled fusion. And just in December, they got to the point where more energy comes out than arrived at this capsule. And they do simulations of the materials in these things using DFT. But they only have ground state functionals. So they always wonder, is the functional accurate enough? The fact that we don't have temperature dependence in it, is this messing up our simulation? And by doing a lot of sort of deep theory about exchange correlation holes and using this conditional probability DFT, Johnny was able to calculate how it changes with temperature. And already people in Germany and other places are taking our preliminary results and running calculations to see how they change, even though we haven't quite finished the paper. That's different. Okay. So to summarize, so DFT is obviously thriving, right? And keeps getting bigger and bigger. As computers get bigger and cheaper, right? DFT just becomes more and more important. This will just keep on going, where people want to do things with simulation rather than the cost of the experiment. There's many different avenues still to be explored, and there's lots of value to improving the functional. Thank you for your attention.